Hi, chemistry students. I'm going to go through today just what you can expect for the test tomorrow. So I'm going to tell you everything you need to know. I know it's a little different and weird when you have to we don't have that review time in class, and a lot of this you learned through videos at home. So I'm going to start, this is over chapters 4 and 5. I'm going to start with chapter 4. And just kind of a quick review of, so the first part of the test is going to be matching, and I'm going to give you some of the names of people who made important discoveries about atomic structure, such as Rutherford. Remember, he did the gold foil experiment and proved kind of that existence of the nucleus. J.J. Thomson, who used a cathode ray tube to prove the existence of negative particles, which we now call electrons. The Democritus, who was that ancient Greek who said, hey, I think everything's made up of these little particles. We call them earth, air, fire, and water, and in different proportions they make up all the different things in the known world. Of course, you should know what an atom is. Let's see. You should know what an atom is. Dalton's theory is actually pretty important. It outlines most of what we believe still today. Let me move this really quickly. Most of what we still believe today, or accept today, all elements are composed of tiny indivisible particles. Atoms of the same element should be identical. That's obvious, right? And different atoms of different elements are different. Atoms of different elements can physically mix together, or they can combine in whole number ratios in those chemical reactions. The only one that is a little bit different, I'm going to make this a little bit larger so you can see the bottom. I'm working one-handed here. The only one that we would say has changed a little bit is that very last one that says chemical reactions occur when atoms are separated from each other or joined. True, or rearranged. Atoms of one element are never changed into atoms of another element as a result of chemical reactions. And we said now we say ordinary chemical reactions because we do know that in nuclear reactions, that's exactly what happens. There's a whole theory about it. So obviously he had no way of knowing that. You should be able to explain in great detail the properties of protons, neutrons, and electrons. Not just what they are in their charge, but these other postulates that are here are other important points. J.J. Thomson already mentioned. Robert Millikan figured out the charge of electrons. Goldstein figured out protons, and Chadwick is the one who figured out that there were neutrons and so on. Rutherford's gold foil experiment was really important, not in discovering new particles, but in discovering that there's a nucleus, and so there's all the mass seems to be in this dense center. That was important. Isotopes. We should be able to, let me just peek at my finger. I think about that a lot more now. You will, so the test is, as I have it written right now, 3 pages. In the word bank on the first page, I'm just going to tell you, and we'll talk about these a little bit more in a little bit, but you should, in the word bank, there will be the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Those are all about that quantum mechanic, quantum theory from chapter 5 that says here's where we're going to find the electrons. These are the rules that govern the order that they fill. So that will be part of the word bank. And then Rutherford, J.J. Thomson, Democritus will be part of this word bank. And then the photoelectric effect. So the end of chapter 5, we just briefly mentioned that. The electron cloud, that's one of the changes in the way we think of electrons and where we find them. We used to say Bohr's model was those concentric rings like planets orbiting the sun, and we now know that's not really accurate, so we really think of it as more of an electron cloud model. We talked about that. Electron configuration, what does that mean when we say, electron configuration? We're basically mapping out where those electrons are, and then as I mentioned, the atom. Okay, so those are the words that you will find in the word bank. Also, the numbers of electrons that we find in the different, and I know we talked about this, but it's worth review here. The maximum number of electrons that we find in each energy level. I'm actually going to look at the periodic table because I think that's probably the easiest way to look at that. So remember, get rid of this. Remember when we looked at how these are. Okay, I'm going to write with my mouse, so this is going to be super messy. So this is my, this is my S block. I'm trying to outline these. This is my S block. All right, so, and I didn't label all of these, so again, this is my S block. This is the P block, this whole block over here. Helium really fits over here. This is the D block. You should have this labeled on your periodic table, and you can use that on the test. And this is my F block. So when I talk about energy levels, in the first energy level, there's only 2 electrons, the 1s1 and helium with the 1s2. Okay? The second energy level has a 2s, second energy level, that's why there's a 2 in front of here, and the 2p. Okay, so the second energy level has an S sublevel and a P sublevel, and it holds 1, 2, 3, 4, 5, 6, and then 7, 8, holds 8 electrons. The third energy level has a 3s, a 3p, and a 3d. So we have 2 plus 6, which is 8, plus 10, which is 18. So that third energy level really holds 18 electrons, and so on. So when we say energy level, that's what we're talking about, the coefficient in front of that S, P, D, and F. You should be able to give me, if I give you an element, you should be able to tell me what the electron configuration of that element is. When we talk about, so usually the difference between orbitals and sublevels. So this is the 2p sublevel, but remember there's 3 orbitals in here. Each orbital can only hold 2 electrons. There's a 2px, 2py, and 2pz in there. Make sure you understand from the periodic table, and you should from the last chapter, what the atomic number and what the atomic mass number means for an element. And then there's some questions on waves and wavelength. You'll have to do some of that calculations, like if I give you the frequency and we know the speed of light, and I'll give you that number as well, so you don't have to memorize it. 3.0 times 10 to the 8th meters per second is the speed of light. We use that in that equation. And so that you should be able to do those calculations, and we did several of those when we talked about wavelength and so forth. So this is the, and you can use this little kind of the wheel cheater, but this is the equation. C stands for the speed of light. We always know that number, and if you're given one of these other numbers, it's pretty easy to perform those calculations. Make sure you understand, like, as wavelength increases, that means frequency decreases. If frequency increases, wavelength decreases, and so hopefully that, and I have a nice visual there of that as well. And then I also have a second small, oh look, I'm on the radio. I also have a second little word bank that goes through the terminology for calculating waves. So wavelength, amplitude, and frequency. So the definition of what those are. And then I've also added into that word bank the equations for, or the word ground state. So you should understand that's what ground state is. And then the Heisenberg's uncertainty principle, just because, and I know we don't talk a lot about that. It's one of those really fundamental things that you just hear over and over again in certainly in physics and also in chemistry when we talk about electrons. So Heisenberg uncertainty principle just says, you can either know where something is or how fast something is moving, but it's impossible to know both at the same time, because if you're measuring one of those things, then the other one is not measurable. And I mean, it's just, if you just know the definition, you're fine. De Broglie also is in that word bank. So de Broglie is this, the guy who said, hey, all matter actually can exhibit wave-like properties. It's just that in larger objects, the wave is so negligible that it's almost immeasurable, that it's just, you really can't detect it, but just trust us, it's there. So you will have to understand how isotopes differ from each other, those varying numbers of neutrons. The other thing that you will have to do on the test is you will have to calculate average atomic mass. So if I give you some fictitious element, I will give you the atomic mass number in AMUs, and I will give you the percent abundance, and you have to know how to set this up. So you have to say, oh, well, this one has this atomic mass, this one has this atomic mass. The one with this atomic mass is present in this percent abundance. The one with this atomic mass is present with this percent of abundance. Just know that you have to convert these percents into actual numbers. So you move the decimal over 2. So it becomes 0.7577. This one becomes 0.2423. You multiply these across. You can answer for this one and answer for this one. Then you just add them up. Do not divide by 2. That was speckle on my face. Do not divide by 2. If you do it this way, you're already you're already accounting for that average this way because you're multiplying by the percent abundance. So don't divide by 2 or divide by 3, kind of a thing. You just simply multiply these across and then you add them up. That should be it. Again, you will have to do some electron configuration, the 1s2, 2s2 kind of stuff. And a couple of problems of calculating either wavelength or frequency, and I think that's it. So hopefully you'll be feeling confident tomorrow. Please work through the study guide. That really will help you. And yeah, let me know if you have any questions.